Chapter 1, Real Numbers and Algebraic Expressions. Section 1.1, the real number system. First, let us talk about sets of numbers. The natural numbers, sometimes also known as the counting numbers. These are the numbers 1, 2, 3, etc. And so these three dots, called ellipses, it just mean that we continue with the same pattern. This set of natural numbers is denoted by the letter n for natural number. The whole numbers denoted by the letter w for whole numbers include the number 0 and the natural numbers 1, 2, 3, etc. The integers denoted by the letter z for the German word for number, Zahlen. These include the negative integers, -1, -2, -3, etc., 0, and the positive integers, 1, 2, 3, etc. And so I have here the, oops, um, negative integers, zero, and the positive integers. So sometimes we call the natural numbers the positive integers. The whole numbers as the non-negative integers. These are integers that are not negative. The rationals, denoted by the letter Q for the Latin word for number, quora. This consists of the set of all fractions, all numbers that can be written as a ratio P over Q, where P and Q are integers and Q is not equal to 0, so that we don't divide by 0. These are numbers which terminate with a repeating decimal. For example, the number 2/3 is a rational number. The number -8 is a rational number. I can write it as -8/1. And so any um, natural number, any whole number, any integer can be thought of as a rational number because I can always write any of whole number, natural number, uh, integer as that number divided by 1. Let's say 4.8371717171, etc. That is a rational number because I repeat 71 forever. We denote this fact that I'm repeating this decimal forever as follows. I'll write 4.83, and then I'll write the 7-1, and I'll put a little line over the 7-1 to indicate that the 7-1s repeat forever. Another example would be the square root of 9. That is a rational number because, well, the square root of 9 is 3, and I can write 3 as 3/1. Irrationals. The irrationals are denoted by the letter Q with a little dash, meaning that it's not rational. So these are numbers which do not terminate with a repeating decimal. So, example. Example of a irrational number would be, well, the square root of 2. And so the square root of 2 cannot be written as the ratio of two integers. And if you try to do that, if you suppose that that were true, you're able to come up with a contradiction. Similarly, and so this means that if you had a square where each side had a length of 1, then those disappeared. Then the diagonal of this unit square would have a irrational length. So irrational numbers occur a lot. As a matter of fact, if you take the square root of any natural number which is not a perfect square, then the square root will be irrational, such as the square root of 6. The square root of 9, of course, is not irrational because 9 is a perfect square. As a matter of fact, if you take the cube root of any natural number, which is not a perfect cube, then this quantity will be a irrational number. So such as the cube root of 5. As a matter of fact, if you take the nth root of any natural number that's not a perfect nth power, then it will again not be, it will be a irrational number. It will not be rational. Similarly, the symbol pi, which stands for the ratio of the circumference of a circle to its diameter, that is not a rational number. It is irrational. If you try to write the decimal representation for pi, you would notice that it goes on forever and it would never terminate with this repeating decimal expansion. Similarly, let's say 4.1234, etc., where they keep where it's a pattern, but it's not a repeating pattern. So it doesn't the exact numbers don't repeat. So it'd go 1, 2, 3, 4, 5. Let's say one. Actually, maybe I'll do this. I'll say 0, 1, 2, 3, 4, 5, 7, 8. Oh no, let's do this so that it will 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, etc. Okay, so you'll have 4 fours, 5 fives, 10 tens, etc. And so that will not be a repeating decimal because you never have the exact same pattern repeating over and over again and of the same length. So you don't have, like a 71 repeating forever and ever. And so because of that, that's a irrational number. Similarly, in the future, in Math 125, we'll discover another symbol, E, and that will be an irrational number. Just like the number pi, the symbol pi stands for an irrational number. The letter E will stand for irrational number, and we will discover this in Math 125. So you may not have seen it yet, but you will see it in the future. The real numbers. So the reals, denoted by the letter R, standing for, I guess, the real numbers. So these are numbers with a decimal representation. In this course, we will basically be looking at, always be looking at real numbers, except for a few cases where we'll only consider, maybe rational numbers or integers, or we may consider what are called complex numbers. But most things in this course will be we'll be looking at real numbers. And so let me give you examples of things that are not real numbers. So if I take something like, let's say 5 divided by 0, this is not a real number. It is, well, undefined. You can't divide by 0. Okay, we'll usually use this shorthand notation for undefined. Similarly, 0 over 0, that's undefined. And let's say 0 over 0 to the power 0, that's undefined. Maybe I'll actually write it out. These are actually sometimes also called indeterminate. Because you can assign more than one value to this particular object. Square root of -9. This is also undefined for right now. Okay. It turns out that in the future, we'll be able to define it. So in Math 125, this will be a complex number. So that's in Math 125. So later in this course, we'll be able to find that. Okay, so we can look at all these number sets and get a relationship between them. And so let's look at these visually, a visual representation of their relationships. And so let's consider this set here as the real numbers. Well, they would consist of the irrational numbers and, well, the rational numbers. And so a real number is either going to be rational or irrational. And so there's a whole bunch of irrational numbers and some rational numbers. The every integer will be a rational number. Every whole number will be an integer, which is also a rational number, which is also a real number. Every, let's see there, natural number is a whole number, which is also an integer, which is also a rational number, which is also a real number. And so that is a visual way to look at the relationship between each of these numbers. Let me do some problems, let's say on page 12. Let's say problem number 2. 5/4, 9/7, -1.5, -2, -1. Okay, so 1 second. And so we want to determine which of these okay. Let me read the instructions for this. In exercises 1 through 4, identify which numbers are A, whole numbers. And so which of these numbers listed above are whole numbers? Well, 5/4, 9/7, negative 1.5, negative 2, and negative 1, none of those are whole numbers. So there are no whole numbers. B, integers. And so let's find which of these are integers. Well, the integers include negatives, and so, but they don't include the fractions or decimals. And so 5/4, 9/7, negative 1.5, those are not integers, but negative 2 and negative 1 are integers. C, which of these are rational numbers? Well, that includes any of the fractions, 5/4, 9/7, and these negative 1.5. A negative 1.5 can be written as negative 3/2. It is can be written as a fraction, so it's a rational number. It is negative 1.5, so it terminates. It has a terminating decimal, and so it is a rational number. Negative 2 and negative 1. Again, these are rational numbers because they terminate. The decimal terminates. It's just ends all in zeros. And so these are all rational numbers. Let me do problem number 3. So I have this set 1.4, negative 1, 5, 7, 4/5, 11, 1 over 11. Okay, and so I want to find which of these numbers listed above is a whole number. Well, 1.4 is not a whole number. Negative 1, that's negative, so it's not a whole number. 5 is a whole number. 7 is a whole number. 4/5 is a fraction, it's not a whole number. 11 is a whole number. 1 over 11, again, is a fraction, is not a whole number. And so these are my whole numbers. B, I want to discover which of these are which of these are integers. And so 1.4 is a decimal, it's not a integer. Negative 1, 5, 7 are integers. 4/5, fraction, is not an integer. 11 is an integer. And 1 over 11 is a fraction, it's not an integer. And C, which of these are rational numbers? Well, 1.4 is decimal, so yes. Negative 1, 5, 7, those are integers, so they're rational numbers. 4/5, fraction, is a rational number. 11 is a whole number, so it's a rational number. 1 over 11 is a fraction, so again, it's a rational number. So everything listed was a rational number. Okay. Let me do problem number 8. Vehicles available in a dealership for sale. In exercises 5 through 8, identify the appropriate set of integers for the following list: whole numbers, integers, rational numbers. And so if I am looking at vehicles available, well, you can't have negative vehicles available, so it would not be integers, would not be appropriate. Neither could you have a fraction of available, and so of a vehicle available. So it's not a rational number. They are whole numbers. So you can either have no cars available, 1, 2, 3, 4, etc. cars available. Next, the number line. A convenient vehicle to visually represent the set of all real numbers is to represent it on what's called a number line. And so for a number line, you would just draw a line. You would then arbitrarily pick a point, call that point the origin, 0. You would then arbitrarily pick another point to its right, to the right of the origin, and you would say that that is 1. You would then use that same distance from the origin to 1 to then write other integers. And so if you go to the right, you'll just put down the integers 2, 3, 4, etc. If you go to the left of the origin, you put down the negative integers, -1, -2, -3. And if there are some rational number, then you would subdivide the distance between two particular integers to put that particular rational number on the number line, whatever fraction it is of the distance between the two integers. If it's irrational, then you would, as close as possible, put it in the correct location. So let me do, let's say, problem number 9. Graph the numbers on the number line. And so -4, 2, 1, 3.5, 4.25, and -3. Okay. Well, note the following. 4.25 is the same as 4 1/4. And so 1 divided by 4 can be written as 0.25. And so now let's try to draw these on a number line. So I'll arbitrarily put a 0, 4.25. That's too far. Let's arbitrarily put, so I'll say that this is 0. Okay, so that's 0. And then I've measured these out to the same distance, hopefully. -1, -2, -3. Oh, I have a -4 there too. Oh, so I've got to go a little, so it didn't matter. I had to go further anyway on this side. Okay, so now I have a -4. So let me put a little dot here at -4, +2, +1, 3 halves. So I go halfway between 3 and 4, and so halfway between 3 and 4 is 3.5. 4.25, that's a quarter of a distance between 4 and 5. So I do halfway, and half of that is 4.25 and -3. Okay, and so maybe I should denote the fact that this is 3 1/2 and this is 4.25. Maybe I should change their color. I'll make them red. Okay. And so those are the particular numbers located on a number line. Note that I can create an order. Um, and so I can say that A is less than B if A is to the left of B on the number line. Okay. Let me do problem number 11. In exercises 11 through 26, determine whether or not the statement is true. Is 5 greater than or equal to 4? Well, sure. 5 is larger than 4, so this is a true statement. Let me do problem number 16. One fourth less than 1/2. Well, is 1/4 smaller than 1/2? Is a quarter less than a $half? Sure. So this is true. Let me do problem number 18. 5 is less than or equal to 5. Well, is 5 less than 5? No. But is 5 equal to 5? Yes. So therefore, this is a true statement. Let me do problem number 21. -1/3 is less than -1/2. Okay. And so if I look at -1/3, actually maybe I'll put this on a number line. And so I go 1/3 of the way out. It's about here. And I go half, well, halfway in between, closer to that. Is -1/3 less than -1/2? No, it's greater. So this is false. So just looking at our number line, I can see that negative 1/2 is less than negative 1/3. Okay, let me do problem number 29. In exercises 27 through 42, find the opposite of the given number. So let's the opposite of negative 6.32. Well, that's the same number but with the opposite sign, so a positive 6.32. We sometimes call the opposite the additive inverse. So the opposite or additive inverse of negative 6.32 is positive 6.32. 33. The opposite of radical 3, positive radical 3, is negative radical 3. Let me do problem, well, let me tell you about absolute value. The absolute value of a number is the distance from that number to the origin on the number line. It is the magnitude of the number it is the positive square root of that number squared I'm assuming here that x is a real number, of course. The absolute value is, well, it's equal to x. If x is non-negative, and it's equal to its opposite if x is less than 0, so that we get a positive answer for x. And so, let me do problem number 40. I want to find the opposite of minus the absolute value of negative 5. Well, the absolute value of negative 5 is positive 5. Therefore, the negative absolute value of negative 5 is negative 5. And so that means that the opposite of the negative of negative 5 is, well, the opposite of, well, we found that this value here was a negative 5. So the opposite of negative 5 is a positive 5. And that's your answer. Okay, so, oops. Let me give you some of the field properties for real numbers. So the field properties. So first let me assume that A, B, and C are real numbers. So I don't have to keep repeating myself about this. Oops. So first let me give you the closure property for addition. So this says that if A and B are real numbers, then A plus B is a real number. And so this says that if you're in this particular set of real numbers, the operation, this function on these ordered pairs of real numbers, still leaves you in this set of real numbers. So this operation keeps you in the same set. And of course that's obvious. If you add two numbers, they're still real numbers. The closure property for multiplication says that if A and B are real numbers, then A times B is also a real number. So again, if you multiply two real numbers, you still get a real number. Commutative property for addition says that if A and B are real numbers, then A plus B is the same as B plus A. So if you're adding two real numbers, the order in which you add these two real numbers doesn't make any difference at all. You get the same answer where if you add 2 plus 3 or if you add 3 plus 2. They'll both give you the same answer. The commutative property for multiplication says that if A and B are real numbers, then A times B is the same as B times A. And so if you're just adding or if you're just multiplying, then the order in which you add or multiply two real numbers doesn't make any difference. Similarly, I have the associative property for addition. Which says I can add A plus B to C, and that's the same as adding A to the sum of B and C. And so grouping, if you're only adding, then grouping doesn't make any difference. Similarly, I have the associative property for multiplication. which says that the product of A and B multiplied by C is the same as A multiplied by multiplying the product of B and C. And so, if I'm only talking about multiplication, then it doesn't make any difference the grouping of these factors. The existence of an additive unit or additive identity. The existence of 1. And so, additive. The existence is 0. There exists a real number denoted by 0 called the additive identity such that for every real number A, we have that A plus the additive identity is that original number A. And so this is a right additive identity. And similarly, by the commutativity of addition, I have that the additive identity plus any number A is that same number A. And so this is also a left additive identity. The existence of a multiplicative identity the existence of 1. There exists oh, and I guess this number 0 is unique, and that can be shown by the previous properties. There exists a real number 1 called the multiplicative identity and again it can be shown that it's actually a unique number such that for every real number A, we have that oops, we have that any number A times the multiplicative identity is just that original number A. And so this is a right multiplicative identity. And by commutativity property for multiplication, we have that the multiplicative identity times any number A is just that same number A. And so this is a left multiplicative identity also. And again, this can be shown to be unique. Next, the existence of an additive identity. Sometimes also called the opposite of a number or the negative of a number. For every real number A, there exists a real number. We'll denote it by minus A, called the additive inverse. Oh, what? Called the additive inverse. That was a typo. Called the additive inverse of A, or called the opposite of A, or the negative of A. Such that A plus its additive inverse is the additive identity. And so this is a right additive inverse. And by commutativity, for property for addition, we have that the additive inverse of A plus A is just the additive identity. And so this is, again, a left additive identity, additive inverse. Let me do next the existence of a multiplicative inverse, also called the reciprocal. So for every non-zero real number A, there exists a real number one over A called the multiplicative inverse of A, and this has the following property. So such that any number A, any non-zero number A, times its multiplicative inverse is just equal to multiplicative identity. And similarly, by the commutative property of multiplication, I have that the additive inverse of a non-zero number A times the original number A is just the additive identity. And so it's a left multiplicative inverse. I hope I said multiplicative. So let me start this over again. Any non-zero number A times its multiplicative inverse is equal to the multiplicative identity. Therefore, this is a right multiplicative inverse. The multiplicative inverse of a non-zero number, real number A, times the non-zero real number A is just the multiplicative identity. And so this is a left multiplicative inverse. So I've given you a whole bunch of properties. The closure property for addition multiplication, the commutative property for addition multiplication, the associative property for addition multiplication, existence of identity for multiplication addition, existence of inverse for addition multiplication. And so these were all paired together. There were a property for addition and a corresponding property for multiplication. Now I want to tie these two operations together. And so we have what's called the distributive property. We have that multiplication distributes over addition, but not the other way around. And so I have that A times the sum of B and C is the same as the sum of the product of A and B with the product of A and C. Similarly, the sum of A and B multiplied by C is the same as the sum of the product of A and C with the product of B and C. Let's do some further examples. Let's say problem number 43. In exercises 43 through 51, complete the statements demonstrating the identity property. And so I have blank plus -8 equals blank. And so we want to show the identity property. And so this is addition. So we want to show the identity property for addition. And so I have, oops, let's get rid of that. And so I have 0. And so I have 0 plus -8 is equal to -8. And that is your answer. Let me do problem number 46. -5/6 plus blank equals blank. So again, this is addition. And so -5/6 plus 0 is -5/6. Let me do problem number 47. -19 times blank equals blank. Well, again, this is multiplication, so I want the multiplicative identity, 1. Negative 19 times 1 is negative 19. Let me do problem 48. 1 times blank equals blank. Well, 1 times 1 equals 1. 51. Blank times negative 2/3 is blank. Well, again, this is multiplication. And so 1 times negative 2/3 is negative 2/3. Let me do problem number 53. 3 plus negative 7. In exercises 52 through 61, complete the statement demonstrating the commutative property. So we want to, in this case, this is addition. So I want the commutative property for addition. So negative 7 plus 3 is the same as 3 plus negative 7. Let me do problem number 55. Negative 6 plus negative 8 by the commutative property is the same as negative 8 plus negative 6. The commutative property for addition. Let me do problem 58. Negative 3 times negative 7 by the commutative property of multiplication is the same as negative 7 times negative 3. Let me do problem number 61. Negative 6 times negative 1/3 by the commutative property of multiplication is the same as negative 1/3 times negative 6. Let me do problem number 63. 4 plus 6 plus negative 2. In exercises 62 through 69, fill in the blanks so the resulting statement is an example of the associative property. So the associative property just says, well, grouping doesn't make any difference. And so this is the same as 4 plus 6 added to negative 2. And that is your answer. Please note that this is a parentheses, and so is this. So just the fact that it's a square bracket or even a curly bracket doesn't make any difference. They're all parentheses. They're the same type of parentheses. It's just they look different. We just visually represent them differently, but they're exactly the same type of parentheses. Let me do problem number 67. Negative 2 times 4 times negative 8. So we have multiple parentheses just for readability, but they mean the same thing. So by the associative property for multiplication, I can regroup these multiplications. So this is the same as negative 2 times 4 multiplied by negative 8. Let's do problem number 69, 61, plus a negative 2/3, plus negative 5 and 1/6. By the associative property for addition, this is the same as 61 plus negative 2/3 plus negative 5 and 1/6. And so you can change the grouping for this sum. Let me do problem number 71. Negative 19 times blank equals blank. In exercises 70 through 77, complete the statements demonstrating the inverse property. So this is multiplication, so let's multiply by the multiplicative inverse. 1 over negative 19. So negative 19, sorry. Negative 19 times 1 over negative 19 is just equal to 1. Let me do problem number, let's say 73. Negative 5, 6 plus blank equals blank. And so this is an addition, so we'll add the additive inverse. The opposite of negative 5, 6 is positive 5, 6. And so negative 5, 6 plus 5, 6 is 0, the additive identity. Let me do problem number 77. Blank times negative 2/3 is equal to blank. So again, this is the inverse property. And so let's take the multiplicative inverse of negative 2/3, which is a negative 3/2. Negative 3/2 times negative 2/3 is the multiplicative identity 1. Let me do problem number 78. 4 times 1/4 equals 1. In exercises 78 through 84, identify the property demonstrated in the statement. Okay, and so this is the, I'm multiplying a number by its reciprocal to get 1, and so this is the multiplicative inverse property. Since the multiplicative inverse of 4 is 1/4, which gives the result of the multiplicative identity 1. So this is the multiplicative inverse property. Let's do 79. Negative 7 plus 7 is 0. And so we have the multiplicative inverse, the additive inverse of negative 7, which is positive 7, added together to give me the additive identity. So this is the additive. I'm adding the opposites to get 0. So this is the additive inverse property. Let me do problem 84. One and 2/3 times 3/5 is equal to 1. Since I'm multiplying two numbers together to give me 1, the multiplicative identity, then these factors must be multiplicative inverses of each other. Therefore, this is the multiplicative inverse property. Let me do problem number 85. In problem 85, it says compute 4 minus 7 minus 5. So let's compute that. Well, 7 minus 5 is 2. 4 minus 2 is 2. And compute 4 minus 7 minus 5. 4 minus 7 is a negative 3. Minus 5 is a negative 8. Sorry. To verify the subtraction is not associative. Well, therefore, obviously 2 is not the same as negative 8. And so 4 minus 7 minus 5 is not the same as 4 minus 7 minus 5. So therefore, subtraction is not associative. And so grouping does matter if you're dealing with subtraction. That's why these properties that I gave you, I just talked about addition and multiplication. Similarly, let's do problem 87. Compute 4 minus 7, negative 3. Compute 7 minus 4, positive 3. To verify that subtraction is not commutative. Well, negative 3 is not the same as 3. And so that says that 4 minus 7 is not the same as 7 minus 4. So subtraction is not commutative. And that's why we talked about these properties of addition, not the properties of subtraction. Let's do problem 89. 45. Compute 45 divided by 5 divided by 3. So this is the same as 45 divided by, well, 5 divided by 3 is 5/3. But dividing by a fraction is the same as multiplying by its reciprocal. 3 over 5. Let me write 45 is 45 over 1. Well, 45 divided by 5 is 9, times 3 is 27. And 45 divided by 5 divided by 3 is, well, 45 divided by 5 is 9, divided by 3 is 3. Well, 27 is not the same as 3. And so 45 divided by 5 divided by 3 is not the same as 45 divided by 5 divided by 3. And so division is not associative. And so this is why we talked about multiplication when looking at all the properties and not division, because these properties I gave you don't work for, don't hold for division. Let me do problem number 91. Compute 45 divided by 5. 45 divided by 5 is 9. Compute 5 divided by 45, which is 1 over 9. Well, 9 is not the same as 1 over 9. And so 45 divided by 5 is not the same as 5 divided by 45. And so division is not commutative. And so we talk about the properties for multiplication, the properties for addition. We do not talk about the properties for subtraction, the properties for division, the field properties. Let me do problem number 93, which says 4 divided by 36 plus 8. Well, 36 plus 8 is 44. 4 divided by 44 is 1 over 11. Let's compute 4 divided by 36 plus 4 divided by 8. Well, 4 divided by 36 is 1 over 9. 4 divided by 8 is 1 over 2. A common denominator for 9, 1 over 9 and 1 over 2 is 1 over 18, is 18. So let's multiply and divide by 2. Multiply and divide by 9. So I get 2 over 18 plus 9 over 18 is 11 over 18. So notice that one over 11 is not the same as 11 over 18. And so division does not distribute over addition. So I have that 4 divided by 36 plus 8. This is not the same as 4 divided by 36 plus 4 divided by 8. And so division does not distribute over addition. Okay. Let me do problem number 95. Negative 4/5 times negative 5 over 4 equals 1. In exercises 95 through 103, identify the property demonstrated: commutative, associative, identity, inverse, distributive. Okay, and so I have the product of two objects equals the multiplicative identity, so this is the multiplicative inverse property. Since since one of the factors is the multiplicative inverse of the other factor, so that their product is equal to the multiplicative identity. Problem number 96. 11 times negative 5 plus 2 equals negative 55 plus 22. So this is the distributive property. The property that multiplication distributes over addition. 97. Negative 4 s minus t equals negative 4s plus 4t. Again, this is the distributive property. The fact that multiplication distributes over addition. Problem 98. Negative 4 times 5 times 2 equals negative 4 times 5 times 2 times, oh, there must have been a negative 2 in here somewhere. That must be a negative 2. Times negative 2. Okay, and so this is the associative property. We are changing the grouping of these things, these numbers, and we're multiplying. So this is the multiplicative, well, associative property for multiplication. $99, 0 plus 1/2 equals 1/2. So we're adding 0 to something and remaining and getting the same thing back. So that's the additive identity property. The fact that 0 is our additive identity. 100. Oh, 0. Well, forget I said that. 0 plus negative 1/2 equals negative 1/2. So again, this is the additive identity property. 101. Negative 4/5 plus 4/5 is 0. So I'm adding two things together to get 0. And so this is the additive inverse property. Problem 102. Negative 1 plus negative 2 plus negative 3 equals negative 1 plus negative 2 plus negative 3. So again, this is associative property because we're regrouping, and so this is associative property. For addition. And lastly, problem number 103. 5x plus y plus 1 equals 5x plus 5y plus 5. Well, this is the distributive property. But it's also the associative property, because you actually have to use the associative property also. So, and the associative property for addition. Oops. Because 5x plus y plus 1 is equal to 5 x plus y plus 1, which is equal to, by the distributive property, 5. So this is the associative property. Of addition. And this is equal to 5x plus y plus 5 times 1. So that's a distributive property. Which is equal to 5x plus 5y, again by distributive property. And 5 times 1 is just 5. I guess there's another one. And so this is by the associative property, by distributive property. And this actually is 5 times 1 is 5, and that's actually the additive identity property. So maybe I should have said that too. And additive identity along with the associated property for addition. So I guess there's really like three properties that we used here to go from one to the other. It's mostly distributed property, but the other two also. Okay, so that finishes off